Okay, in this segment we're going to be starting to talk about um, a very important circuit called the differential pair. And this circuit will basically form the input stage of the operational amplifier and various other circuits that are related to it. It is one of the most important circuits that we will study this semester. And we will, of course, be at this stage talking about it in terms of a Mos differential pair made from N-Mos transistors or P-Mos transistors. But the same circuit can be implemented with bipolar transistors and often is implemented with bipolar transistors. It's also a topology that dates back to the days of the vacuum tube. So it is a venerable circuit that has been in many commercial products, many op amps, many other kinds of products like analog multipliers and other kinds of circuits. And so to recognize, we will be studying it as the CMOS circuit, but it also has much wider use than that. So to start with, we're going to actually start with, to develop the idea, we're going to start with a source follower. Okay, so if you haven't watched the videos on the source follower, obviously you should probably stop and go back and do that, since it's going to be sort of a building block for us here. So this was our source follower, Vn, Vb, and Vout. And Nb was setting up a bias current that flowed in the source follower transistor. And under normal circumstances, that bias current is the current that flows in MSF. Suppose we add a second transistor to the circuit with the gate connected to ground and the drain connected up to VDD. And let's suppose Vn is something, like 2.5 volts. And Vb is maybe around the threshold voltage, like maybe 0.7. So what do we know about this voltage here, V out? Well, before we added that transistor, the second transistor, V out was given by kappa times Vn minus Vb. And so let's say, for the sake of argument here, our numbers that we've assumed here give us 2.5 volts minus 0.7 volts, which is going to be 1.8 volts. And let's say kappa is, 2/3 or 0.66. Which would give us something like 0.66 of 1.8 volts, which is going to be 1.2. This is going to be about 1.2 volts under these circumstances. So the question is, how much current is flowing in the second transistor? Under these circumstances? And how did adding, so this is 1.2 volts is, let's say, before we added the transistor here. And suppose we add the transistor at this point. How much current is going to flow in that second transistor, and what effect is that going to have on the circuit? Okay, so we have an N-Mos transistor. Its source is down here because this is at the lower potential than the two terminals here, or of the two terminals. This one's up at VDD. So this is the source at 1.2 volts. This is the drain at VDD. And the gate is at ground. So this has negative 1.2 volts of VGS. So the question is, how much current is going to flow in this second transistor? The answer is practically none, right? So there might be a few femtoamps of current or something like that, but it's really small. So for all intents and purposes, this is like about zero. Much less than, let's say, the microamp bias current level that we have. So we really haven't changed the situation. So we know a lot about what's going on in this circuit, right? Based on our discussion of the source follower. Suppose we start increasing this input up from ground. Let's say we make it 0.1 instead of 0. Is the situation any different? Well, not really. We still have minus 1.1 volts of gate to source voltage, and that's not going to give us any channel current. In fact, we can bring this up considerably. We can say, well, what about 1.2 volts on the gate? All right. Don't want you to go to sleep. Okay, what about 1.2 volts? Well, here, the gate to source voltage is 0. Right, so plus minus 0 volts. And at 0 volts VGS, we still have very little current flowing. Right, so the question is, when are we going to start carrying current in this transistor? I mean, suppose I make it 1.5 volts on the gate. Well, then we got 0.3 volts gate to source voltage here. Well, how much current flows in the transistor with 0.3 volts gate to source voltage? You know, maybe we're up from 0 down, or up from femtoamps up to maybe a few picoamps. Still very, very small compared to the roughly, let's say, 1 microamp of current that we would have at threshold. Right? So suppose we go up to 2 volts here on the gate, so that we have we would have 0.8 volts gate to source voltage. Well, how does that compare to what we have here? Here we have 2.5, 1.2, that's going to be 1.3 volts gate to source voltage. So we still have a much higher gate to source voltage over here than we have over here. And so the amount of current that's going to be carried by this second transistor is still quite a bit less. I mean, maybe it's going to be up to a nanoamp now. Or maybe even 10 nanoamps, but it's still only like 0.1% or 1% of the current flowing in this transistor. And so it's only when we get up into about, let's say, 2.3 volts or 2.4 volts. Let's say 2.4 where we have here maybe 1.2 volts. Where now we start to get comparable gate to source voltages, and now maybe we're starting to see some shift so that this is not any longer all of the bias current, but now this is maybe, maybe it's 0.8 microamps and this is 0.2 microamps or something. And so at that point this voltage may start shifting, because it's no longer the case that this transistor might as well not even be in the picture. Okay? So by adding this second transistor here, we really don't change anything until this second gate voltage gets to be kind of comparable to this gate voltage. And of course, when they're equal, so that this is maybe 1.3 volts. Now we're assuming here that this hasn't changed. It will actually change in practice. But when these two transistors have equal gate to source voltage, what do we know about their currents? Well, the transistors are operating in saturation, and so the current in saturation is determined primarily by the gate to source voltage. And so they should be equal if they're matched, and that's our typical starting assumption here. And so they should have equal current, 0.5 microamps under those circumstances. Well, what if I then started moving this higher? What would happen then? Well, these two have the same source voltage, so this one would start to have more VGS, and so the current in this branch would start to increase and become larger than the current in this one. Okay? So suppose I don't have these two drain voltages connected to VDD anymore, but they're connected to other things. If the transistors are saturated and they don't have a very significant early effect, does that change anything that we just said? Well, obviously not, because the transistors' drain voltages don't affect the current in saturation. And so as long as those two voltages are high enough so the transistors stay saturated, then the story will be about the same. Okay? So that's kind of an introduction to the basic idea based on the source follower that we had talked about in the last couple of segments. Now we're going to go back and kind of lay out the diff pair and talk about it qualitatively in its own right here. So let's suppose we have two transistors that we will call M1 and M2, very creative, and the two input voltages here to the circuit will be V1 and V2. And there is a bias transistor down here, just like we had in the source follower, which we will call MB, whose job in life is to set up a constant current, IB, that will flow in these two transistors in some way. It'll get split up between these two transistors and it will flow in some way. But this current level controls the overall current that's flowing, the total current that's flowing in the circuit. We have two currents, I1 and I2. And these are the outputs of the circuit. Okay, and we're going to assume that the two drain voltages are held high enough to keep M1 and M2 saturated. We're going to call this common source node down here V. Okay, so these are the diff pair transistors This is the bias transistor. Call this VO1 and VO2. And so our assumptions are going to be typical match transistors, operating at same temp, and VA for the time being is going to be infinite, so negligible early effect. We're going to assume VO1 and VO2 are held high enough to ensure M1 and M2 are saturated. And we're going to say for proper operation, we want MB to be saturated. Current source like. So it should operate like a current source. Okay, so I'm going to suppress the diff pair transistors and the bias transistor labels here. We want to do some thought experiments here to try to understand how the circuit works qualitatively. So first of all, what can we say about the currents? Well, we can say in general that KCL at node V tells us something about the relationship of these three currents, right? So I1 plus I2 is the total current flowing down from the sources of M1 and M2, and that should equal IB. So it says IB is equal to I1 plus I2. That should hold generally. Suppose V1 equals V2. What can we say about the currents in that case? Well, V1 equals V2 implies that I1 equals I2. Right, because they have the same source voltage by the way they're connected, and they're saturated, and so the same gate voltage implies the same gate to source voltage, and that implies the same currents. Right? And so these two things together, 1 and 2 together, imply that I1 will equal I2 will equal half of the bias current. Right, so they will split the bias current 50-50 under the circumstances that V1 is equal to V2. So suppose V1 is larger than V2. What can we say about that? Well, V1 is greater than V2 implies that I1 is greater than I2. Right? Because this one will have more gate to source voltage than this one. And so what that tells us is that IB is less than or equal to I1, greater than I2, greater than, let's say, IB over 2. So it'll tell us that I1 is larger than I2, and since they have to sum to IB, and they're both positive, we have this chain of inequalities here. I1 is going to be bounded by IB. It's going to be bigger than half of IB. I2 is going to be less than half of IB, and I2 will be greater than 0. Right? It may be much smaller than I1, but it will be positive. And we can run this the other way. So if similarly, if V2 is greater than V1, we have I2 is greater than I1, and so we would have IB greater than or equal to I2, greater than half of IB, greater than I1, greater than 0 amps. Okay? So, let's think about sort of step by step, cause and effect. How does the circuit behave in a given situation? So let's suppose that we have V1 equal V2, that balance condition. So let's call, let's say that this is at I don't know, 2.5 volts. So that these two currents are each half IB. And let's suppose we move both of these up together. We make this, let's say, 3 volts. Let's suppose we step them up together, so from 2.5 to 3 volts, very abruptly at some time t. Well, initially, what's going to happen? V1 and V2 now have half a volt additional gate to source voltage over what they had before. This immediately after the step. The source hasn't gotten the memo. It's still wherever it happened to be, right? We could figure out roughly where it is. But the current in each side here is now going to be transiently much greater than IB over 2. Right? So we have more current than IB flowing onto this node. This is operating like a current source, and so it's going to be sinking IB from this node. So the question is, where does that excess current go? Well, the answer is into a parasitic node capacitance. There's some capacitance on this node, and that excess current will flow into this capacitor. The amount by which this current exceeds IB will flow into this capacitor. And that will cause dV dt to be greater than or equal to 0 volts per second, which implies that V is going to go up. V going up will have what effect on these currents? Well, this is the source voltage of both of these transistors. And so that's going to turn down the current level in both transistors. And so eventually, as that current level reduces, we'll get back to IB over 2 on both sides, at which point dV dt is going to be 0 because there's no more excess current to flow into the node capacitance. And so V stabilizes. V achieves a new steady state. But notice the final condition here is the same as it was before. The fact that there's no difference between these two inputs means that the two transistors are going to split the current 50-50. And so we get back to the same baseline. So if we change these two inputs together, we don't get very much change in the currents, at least in the steady state. If we were to change these slowly so that V has a chance to respond and keep up with the situation, then there would be no observable change in these two currents. Okay? So that's the first scenario that I wanted to imagine. Now let's suppose we start out at that same scenario and we only increase one side. So 2.5 volts here, let's say 2.5 volts here. And now we're just going to increase V1, let's say to 3 volts. Well, what happens here? Well, what happens here is that just I1 will be bigger than IB over 2. All right, so its current's going to increase. And so we still have more than IB flowing onto node V. And we still have now some excess current that's going to flow into this node capacitance. So we get dV dt is greater than 0. And so that means V is going to increase. So V increasing now has the same effect as it had before, where we're turning the current level down in both transistors. And so the side that increased initially will start to reduce, but so will I2 start to reduce. And so the net effect is going to be that when the sum of these two currents reduces back down to its original level of IB, that's when this excess current it stops and V stops increasing because dV dt is 0. We're going to have a net increase by some, let's say, delta I on the I1 side, and that will be bought at the expense of a net decrease in I2. All right, so we will have increased I1 by some delta I. We're not saying how much that is at this point, it's just some amount. But because we have to get back to the same level, the amount by which we increase I1 has to be bought at the expense of a decrease, an equal and opposite decrease in I2. So this structure basically steers the bias current back and forth. Right? So if the two voltages are equal, then the current on the left side will equal the current on the right side. If V1 is higher than V2, then we're going to steer more of the bias current over to the I1 side, and less of it's going to be on the I2 side. And since they have to sum to the same, a constant value, we have a zero-sum game here. So whatever the increase in I1 is, that's also the decrease in I2. Okay? So we could play the game, or we could imagine this scenario on the other side, where we had both of them at the same level, and we increase the V2 side. We'd have the same kind of story. I2 would increase now instead of I1. More current flows onto this node than is flowing out from the bias transistor, so this node voltage is going to increase. That's going to push back on the current, turn the current level down in both transistors. So the current in M1 will decrease from its value from IB over 2 down to something below IB over 2. And this current, which had increased above IB over 2, will still maintain itself above IB over 2 when it stops. But now we'll have the current increase over here and the current decrease over here. We could imagine having V1 decrease, and that would turn down the current here in M1 below IB over 2. Well, it's going to have a current deficit flowing onto the node relative to what MB is sinking. MB will then cause current to have to come out of the node capacitance. That will cause a decrease in the voltage here. And that will turn up the current in both sides here, because we're decreasing the source voltage, and that has the effect of increasing the current in the two transistors here. And that will increase the current here above IB over 2 and increase this above its initial decreased value. But the net result would be that the current here would be less than IB over 2 at the end of the day and more than IB over 2 at the end of the day over here. So by allowing this common source node to float up and down so that KCL is satisfied, we have this current steering behavior where the current will be directed to one side or the other depending on which side's gate voltage is higher, which input voltage is higher. So question is, how much of the bias current is it possible to get? Well, you can't get more than all of the bias current, right? So if we steer the current all the way over to one side, the maximum current that you could get out is IB. And so what does this mean? If we were to plot, let's say, these two currents, I1 and I2, as a function of, let's say, the difference between V1 and V2. When V1 is equal to V2, that means that this voltage V1 minus V2 is 0. We would have half the bias current. They will both be at half the bias current. If we make V1 much larger than V2 so that we're over here on the right, then we're going to be at all of IB. Right, so there's kind of this line here that represents a ceiling. And so the current in I1 is going to be all the way over here, and the current in I2 is going to be down here. So this is I1, and this is I2. What about on the opposite extreme? Well, on the opposite extreme, when V1 is bigger than V2, we're down here in negative territory. We're going to have M2 getting all of the bias current, so I2 is going to approach IB, and I1 is going to be approaching 0. And so what we're going to get is something that looks like this, presumably. So the two currents will be equal at the 0 when the difference between the two is 0. And asymptotically, we're going to approach IB over here. Asymptotically, we're going to approach 0 over here. And I2 is just IB minus I1. And so it's just subtracting the I1 curve from the I2 curve to get, or the IB curve to get I2. Okay, very often we'll actually take the difference between I1 and I2 to be the output of the circuit instead of I1 and I2 individually. And in that case, what does that look like? Well, I1 minus I2 would be 0 when I1 is equal to I2, right? And at the most, the difference between the two could be minus IB and plus IB. And so what we need to do is basically flip the I2 curve down and then add the two curves. So when I1 is practically IB and I2 is 0, the difference is going to be basically following I1. When the two are equal, we're going to get something like this. Add 0, and then when we're at this extreme, I1 is 0 and I2 is going to be IB, so I1 minus I2 will be approaching minus IB, and we're going to wind up with something that looks like this. So this is I1 minus I2 qualitatively. Okay, so that's it for this segment. Next time we'll actually try to do a large signal analysis of this circuit and try to find some expressions that relate the output currents to the input voltages. And we'll actually find that for weak inversion and strong inversion bias cases, we can actually make some headway on that. But it's important to try to understand the circuit qualitatively before we start plowing through the math, because not all circuits will yield to the math, but you can still make some good headway at understanding how a circuit behaves qualitatively if you think about it. Okay, so anyway, we'll see you next time.